Hello students, today we'll see minimum cost spanning tree in that Prim's algorithm. What is a spanning tree? First, we'll define what is a spanning tree. A spanning tree of a connected graph is a connected acyclic subgraph. Acyclic means, as we know, there is no cycle formation. It is going to be an acyclic subgraph. That is a tree that contains all the vertices of a graph. All the vertices of a graph will be there, but it is going to be an acyclic. So then we are going to call it as a spanning tree. What is a minimum spanning tree? A minimum spanning tree of a weighted connector. It should be weighted. It should be a connected graph, and it's a spanning tree of the smallest weight. So what we are going to do? We are going to consider the smallest weight of a span. It's a spanning tree of the smallest weight, where the weights of tree is defined as. How do we define the weights of a tree? We are going to take the sum of the weights of all its edges. That is nothing but our minimum spanning tree. The minimum, what is this minimum spanning tree problem? Is the problem of finding a minimum spanning tree for a given weighted connected graph. So what we are going to do here in this problem, we are going to find a minimum spanning tree for a given weighted connected graph. How does our Prim's algorithm works? We'll see now. Prim's algorithm constructs a minimum spanning tree through a sequence of expanding subtrees. Means we are going to add one by one edges, one by one vertices by checking which is the minimum. So what happens here initially? The initial subtree is a sequence which consists of single vertex, which is selected arbitrarily. Any vertex can be selected arbitrarily from a set of v vertices in a given graph. On each iteration, that is on every iteration, what we are going to do, we are going to expand the tree, the current tree, in the greedy manner by simply attaching the nearest vertex. Not that is what we are going to do is, we are arbitrarily selecting one vertex. Once we select that vertex, then we are to add the next vertex. So how do we add that next vertex? The vertex which is nearest to this vertex, that will be added, but it should not be already present in the tree. So then that vertex will be added. By the nearest vertex means the vertex that is not there in a tree, and it is connected to a vertex in a tree by an edge of the smallest weight. So the algorithm, what we are going to do, start with a particular vertex, then go on adding the next vertex. How we are going to add the next vertex? A vertex which is near to this one with a minimum weight that will be added. That particular edge will be added to the tree. The algorithm like this, it will go on working. When it is going to stop, when all the the algorithm stops after all the graph's edges vertices has been included in the tree. In a graph, say assume that there are 5 vertices are there. All the 5 vertices should be added to the tree. Then only the algorithm stops. Since as this algorithm expands a tree by exactly one vertex on each iteration, what it is going to do, every iteration it is going to add only one vertex. So what happens here is the total number of such iterations is n minus 1, where n is the number of vertices in the graph. The t generated by this algorithm obtained will be the edges used for the tree expansion. So what it is going to do in brief, the Prim's algorithm arbitrarily will select one vertex. After selecting that vertex, then it will go on adding the next vertex. How it adds the next vertex? A vertex which is nearer to this current vertex with a minimum cost that will be added. In the next step, again it will be adding the next vertex. Like this, it is going to add all the vertices in a graph to a tree. So that after that, at the end when we calculate, it is going to give the minimum cost. So we call it as a minimum cost spanning tree. This simple pseudocode for this Prim's algorithm is Prim's algorithm for constructing. For what purpose we are going to write this algorithm? For constructing a minimum spanning tree. A weighted connected graph G is equal to V comma E. V represent vertices and E is an edges. The output we are going to have is output ET, the set of edges composing a minimum. What all the edges which are composing a minimum spanning tree, that will be there, and the set of vertices starting from the initial vertex. Initial vertex we are going to consider it as V naught. Initially no edges will be there, so we are going to start with the first vertex, and initially no edges is included. We'll rate it as 5. So for I is equal to 1 to but cardinality of v minus 1 means, so already 1 is added. So n minus 1, as I said, the number of edges you are going to have is, the number of iterations you are going to have is n minus 1. So cardinality of v indicates the number of vertices minus 1 do. Find the minimum weight edge. So as we have seen that, take for arbitrary select one vertex, then you have to select the next vertex which is having a minimum weight. So that's why we will write it as find a minimum weight edge among all the edges u, v, comma u. That is which all are connected to that particular vertex. Among all those vertex, whichever is the minimum, that has to be selected. And u is in v minus vt means vertices which are there in a graph minus which are already selected. So already selected vertices has to be left and remaining vertices has to be included. So we say it as v minus vt. So the set of vertices which are there already there plus whichever is the new one included vertices that will be there, that indicates vt union v star, which is newly included vertices. Same thing when the particular vertex is added from one vertex to the other, that particular edge is also added to the minimum spanning tree. So we write it as et union E star, whichever edge is selected, that vertex, that edge is also added to our set of edges. So that is nothing but your vertices are added as well as the edges are added. So this is how we are going, that is going to return the number of edges. So you see here, we can see here, this is a given graph. The spanning tree is, this should be a connected acyclic subgraph. It's a spanning tree. Minimum means it should take the minimum cost, then we are going to call it as a minimum cost spanning tree. So it is a, I think you can see this one. This is a spanning tree. Here you can see here, v is equal to 6. So here you see all the 4 vertices are there. It is an acyclic, there is no cycle formation. So we are going to get, if we, this is, it should, all the vertices should be included. All the vertices are included. If we calculate, we are getting it as 6. Again, this is also a spanning tree. Here it is also a cyclic spanning tree. So all the vertices are connected. Here the cost is 9. So again, if you see this one, all the vertices are connected. It is a cyclic. Here the cost is 8. These are the different spanning tree for a given graph. So among this, our step is to consider the minimum cost, construct the minimum cost spanning tree. Today we will see the apply the Prim's algorithm to the following graph. This is a given graph. So here, first we have to start arbitrarily select any vertex. First step is arbitrarily select any vertex. I have selected the vertex as A. So once I select the vertex as A, then I have to check which is the nearest vertex to this vertex A with a minimum cost. So here from A to B, see check here, A to B is there, A to C, remaining vertices are B, C, D, E, F. So I have to consider all these vertices and first I have to write among this which one has to be selected, we'll see it. Now A to B, there is an edge with a cost 3. So how do we write here? There is an edge from A to B with a cost 3. So A to C, there is no direct edge. So what we'll do, we'll mark it as an infinity. If there is no direct edge, then we are going to mark it as an infinity. And check A to D, there is no direct edge. So we are going to mark it as dash comma infinity. Then when it comes to E vertex, there is a direct edge from A to E with a cost 6. So we'll write it as 6. When it goes to F, there is also a direct edge from A to F. So what is the cost here? 5. See, if we check among all these things, all these we have calculated from A to B, we have calculated A to C, A to D, A to E, A to F. Which is minimum? A comma 3 is the minimum. That is from A to B, 3 is the minimum. 5. If I go to F, it is 5. If E, it is 6. So among these 3 from this particular vertex, only these 3 has the direct edges. Among these 3, which is minimum? 3 is minimum. So we are going to include that in our spanning tree. So in the first step, started with an arbitrary vertex A. This vertex B has been added with an edge 3. Edge cost on this edge is 3. So in the next step, whichever vertex is added, that will take. Here we have added this vertex to the spanning tree. So B of A comma 3. So now A is done. Now from A to B we have reached. In the next step, we are remaining vertices are C, D, E, F, because from A already we have calculated. So now B to C. I can go, there is a path from B to C with a minimum cost 1. Then next comes D to, B to D. Whether there is a direct edge from B to D, there is no direct edge from B to D, so we'll write it as infinity. B to E, there is no direct edge from B to E, but already we have seen in the previous step, already the A has been included in a spanning tree. We have to write that cost here, that edge here. So from A to E, so see B to E, there is no direct edge, so it is going to infinity, but there is already a direct edge from A to E with a cost 6 that we are going to write here. And B to F, we have 4. B to F, 4 has been written. So again, you check here. Now A to B is done. Now next B to which edge can be added in a spanning tree, we need to check. Here it is, to C it is 1, for D it is infinity. Again from A, we can reach to B, we can reach to E. What is the cost here? 6 is there. So then here it is 4. Among these, which is least here? B to C is least with a cost 1. So what we'll do, we'll include this edge in a spanning tree. So this edge has been included in a spanning tree. So C, B, comma 1. Now A, B, C is done. Now left out vertices are D, E, F. So and then consider the vertex C. From vertex C, I can go to D, I can go to F. So vertex C to D, what is the cost here? 6. That is C to D cost is 6. C to F. C to F, either you can take this one or B to, both the cost is same. So if among this, if one was least, then you would have taken the least one, B to F or C to F. So here both are same. We can take C to F or even the B to F also, which can be taken. Here I have taken it as B to F. But even you can take the C to F also, the same answer will get. Why? Because here both the places the cost is 4 itself. So B to F, and already E, as I said in the previous step itself, there is an edge from A to E with a cost 6. So we are including here, when I consider this vertex D, when we are considering the vertex D, I can include this, I can include this. Here it is 6, here it is 4, whereas E, already there is no direct edge from C. So the minimum already there, this is included. So we'll consider this one, that is E, A, comma 6. Now among these, which is minimum, this is minimum. So we'll consider B, F, B, comma 4, or you can, if you are consider C, comma 4, that also is C, comma F, C, comma 4 is also right. Both are right. You can take this or this. Both of them can be considered. Now next step. F, B, comma 4 is considered. Now you are at the vertex F. So now left out vertices are D and E. So we'll see here D and E. So F to D I can reach. What is the cost? 5. So F to E I can reach. See, now we have two things in front of us. F to E also we can go, and even A to E we can also go. But among these two, which is minimum? This is minimum. So we'll consider this path. See here, from each vertex we should reach to the other vertex. So here F is there. F to E, what is the cost here? 2 is the cost. So what we'll do here? So we'll consider this edge. D to F is 5. E to F is 2. E to F is 2. Oh, sorry, F to E is 2. So among these two, which is least, this is least. So we'll consider this one. So once we consider this one, next we check which all are the remaining vertices here. D and F are there. Among this, which is the minimum here? This is the minimum. So in the next step, we'll consider the vertex E. So now F has been added into the minimum spanning tree. F has been added. So in the next step, we'll get the next one. The next vertex is E. So we'll consider the next vertex E. When we consider the next vertex E, now left out vertex is only D. We need to check. So here we have a different paths. From E I can reach to D. Even I can reach from F to D, even C to D. There are 3 ways to reach to D because all these vertices are already in the spanning tree. So what we need to do here is we have to check for the minimum one. Among these 3, which is minimum 6, 5 and 8, because C is also selected, F is also selected, E is also selected. Among these 3, which is minimum, this is minimum. So F, D to F to D, the cost is 5, that has been selected. So this path will be selected in our spanning tree. You can check here. F to D, this path has been selected. So now all the vertices has been added into the graph, into our tree. So now if you check our the spanning tree will be a spanning tree is of this form. See all the vertices which all we have included are shown with a thicker line: A to B, B to C, B to F, F to D, and F to E. This is our minimum spanning tree. So here you can see. So the minimum span is given by A B B C B F A B B C A B B C C F A B B C B F F D F E, and the spanning tree obtained is given shown below. This is the spanning tree what we are going to get. The cost of this minimum spanning tree is, we have to add all these costs. We'll get the cost of the minimum spanning tree. 3 plus 4. See here, whatever we have here. 3 plus 4 plus 1 plus 5 plus 2. We are going to get the cost of a minimum spanning tree is 15. So this is how our Prim's algorithm works. Thank you.